This is an introduction to Module 11, in which we're going to be looking at homogeneous linear systems. And we'll be looking at two things. We'll be looking at eigenvalues and eigenvectors, and then we'll also be looking at solutions. And the thing is that to find solutions to these linear systems, we're going to depend on finding eigenvalues and eigenvectors. In order to find eigenvalues and eigenvectors, I want to derive briefly here how we do that. If we assume that our solution takes on the form of some vector, some constant vector, times an exponential, and we come to that conclusion being that for systems that are that we saw before that were linear, the solutions included the exponential. So we're going to say, well, what if the solution will be a vector that has an exponential in it? If that were the case, then we can do the following derivation. We take the derivative of that vector that we are thinking might be our solution. We multiply that vector times a, and that's the second line. And then we equate those two, because if they're going to satisfy the differential equation, those two must be equal. And we arrive at this fourth line. Then we set this to 0, and we come up with this equation here. Since e to the lambda t can't be 0, then it must be that the rest of it right here, or a minus lambda I, which is a matrix, times k must be 0. We're interested in non-trivial solutions, meaning that if k was the 0 vector, then for sure the equation would be satisfied. But are there any other solutions than the trivial one? From linear algebra, we know that that's only the case if we can find that the matrix A minus lambda I has determinant 0. So we will find those values of lambda that allow the determinant of A minus lambda I to be 0. Those lambda values we'll call the eigenvalues. And then the vectors k that we obtain by plugging in lambda here and solving this equation, those will be the corresponding eigenvectors. Okay, so there are three cases. The first case is we might say that we're going to restrict ourselves to 2x2 matrices. Suppose that we have two distinct eigenvalues, two different eigenvalues. Well, in that case, we find the eigenvectors corresponding to each of the eigenvalues, say k1 for lambda 1 and k2 for lambda 2, and we can write the general solution in this form. The eigenvector times e to the eigenvalue times t, and then we have two of those, and so that's our general solution. But it's possible that we would have just one eigenvalue that arises. So we have just one eigenvalue that comes from our determinant of A minus lambda I being set to 0. But this is a 2x2 matrix. I know that I need two linearly independent solutions. And so one of them we find in the normal way. Here's k1 e to the lambda 1t, just like we did in the first case. But to find the other solution, we then solve this other equation. We find the vector p that satisfies A minus lambda I times p equals k1, where k1 was the eigenvector that we found for the eigenvalue lambda 1. Once we have that, we can plug it into the equation like this, and we have the general solution as well. Finally, we could have complex eigenvalues, and in this case, they're always complex conjugates. You always have the same value, one with a plus sign, one with a minus sign. And sorry about that. And the process is similar in that we're going to find the vector k, say, associated with the eigenvalue lambda 1. So you choose one of the two eigenvalues. I'm going to choose lambda 1, and I'm going to find the eigenvector associated with it. Then I'm going to look for the real part of k and the imaginary part of k. What I mean by that is if I have a vector k like this, then I can rewrite it in a way so that there's a real vector plus an imaginary vector. So in this case, the numbers that are times I go in B2, and the numbers that are just real numbers go on B1. If I can find those two, then I can write my real solution, or the real solutions are given then by x1 is b1 cosine of beta t minus b2 sine beta t e to the alpha t, where beta comes from the complex number and alpha does too. The general solution would then be c1 times x1 plus c2 times x2. And those are the three cases that we'll see in this section. You should look at the examples to look at them more carefully.